Hey everyone, welcome to This Explainer. Today, we're diving into a genuinely brilliant idea in machine learning: how algorithms actually mimic human learning by continuously correcting their own mistakes. We're going to explore a remarkable family of algorithms known as boosting and specifically look at the groundbreaking algorithm that started the whole movement. If you've ever wondered how machines can get smarter, not just by looking at a ton of data, but by actively hyper-focusing on exactly what they get wrong, well, you are in the exact right place. Okay, here's our game plan for today. We'll start with learning from past mistakes, meet the very first boosting algorithm, figure out how it earns a louder voice, look at updating the focus, and wrap up with the complete learning cycle. All right, section 1, learning from past mistakes. Let's get right into it. So to really wrap our heads around this, we kind of need to throw our traditional ensemble learning mindset right out the window. Think about bagging for a second, like a random forest model. The whole vibe there is letting a bunch of models solve a problem entirely independently. It's literally like a group project where 5 students write their reports completely on their own, no talking whatsoever, and at the very end, the teacher just averages their grades. But boosting? Boosting is a totally different beast. Imagine if instead, the first student writes a rough draft. Then the second student reads that exact draft and fixes the mistakes. The third student takes that updated version and polishes it even more. They aren't isolated at all. Each model builds directly on the back of the previous one. And you know, this isn't just a clever machine learning trick. This is basically how we learn as humans. Think of a football coach getting a team ready for a massive game. You're not going to drill basic passing every single day if the team is already nailing it, right? But if the coach sees the defense completely falling apart on corner kicks in the last match, well, guess what the next practice is going to be about? Corner kicks. You focus specifically on that weakness. And once they get better at that, maybe the coach spots an issue with finishing, so the next session is exclusively about shooting. We don't just start from scratch every day. We adapt and we hyper-focus on whatever weaknesses are left. Moving right along to section 2, meet the first boosting algorithm. So this whole concept was completely flipped on its head back in 1995 with a breakthrough called AdaBoost, which stands for adaptive boosting. Now, here's the part that might actually shock you. AdaBoost relies entirely on what we call weak learners. A weak learner is a tiny, incredibly simple model, often called a decision stump. It's basically a decision tree that asks one single question. That's it. Something like, is the wind speed over 20 kilometers per hour? Because it's literally just asking one question, it performs only slightly better than a coin flip, maybe around 55% accuracy on a yes or no problem. On its own, totally unimpressive. So, why on earth would a cutting-edge algorithm purposely use such a weak model? Well, it all comes down to specialization. Think about building a massive skyscraper. You don't just have one single worker trying to build the entire thing by themselves. You have one team that only lays the foundation. Another team just installs the electrical wiring. Someone else paints the walls. Everyone has one super specific, simple task. If you just look at the electrician's work, it doesn't look like a building at all. But put it all together, you get this extraordinary structure. That is AdaBoost in a nutshell. Each weak learner brings one tiny, highly targeted improvement to the table, and they all cooperate to build an absolute powerhouse of a final model. Which brings us to section 3, earning a louder voice. Okay, so if we have dozens or maybe even hundreds of these weak learners, how do we combine their predictions in a way that makes sense? Do they all get an equal say? Absolutely not. Imagine you've got a panel of doctors trying to diagnose a really complex illness. You've got a seasoned veteran with 30 years of experience sitting next to a resident who literally graduated yesterday. Now, sure, you want to hear both opinions, but you are naturally going to put way more weight on what the veteran says, right? Their track record has earned them that trust. AdaBoost does the exact same thing with its models. It doesn't use simple majority voting where everyone gets a standard vote. It uses weighted voting, meaning the models with a better track record automatically get a much louder voice in the final decision. We measure exactly how much we should trust a learner using a mathematical value called alpha. Honestly, just picture alpha as a giant volume control dial. AdaBoost acts like the conductor of an orchestra, constantly adjusting the volume of every single instrument. If a specific learner is crushing it and performing exceptionally well, the conductor cranks its volume all the way up. But if a learner is struggling and making a mess, the conductor dials its volume way down. Every learner gets to stay in the orchestra, but their influence on the final sound is drastically different. And mathematically, this works out beautifully. An excellent learner with a super low error rate gets a massive alpha weight, a really loud, booming voice. An average learner gets a moderate alpha, so its voice is a bit quieter. But here's the absolute genius part. If a learner is basically just guessing randomly with an error rate right around 50%, its alpha value drops to almost zero. It is essentially muted. This acts as a brilliant built-in safety net, automatically stopping bad models from ruining the final prediction. All right, section 4, updating the focus. So the big question is, how does AdaBoost actually decide which mistakes need more attention in the next round? Let's walk through an example. Say we're looking at a data set of wildfires, trying to predict if they'll cause hazardous air quality. At the very beginning, AdaBooster's going in blind. It knows absolutely nothing, so it starts everyone off on a level playing field. Every single wildfire event gets the exact same initial weight, let's say 0.10. On step 1, every single piece of data is treated as equally important. But let me tell you, that equality does not last long. After our very first weak learner makes its guesses, we check the scoreboard. Let's imagine it totally nails event 1 and event 10, but it completely bombs on event 4 and event 9, which happen to be these weird, tricky coastal wildfires. AdaBoost reacts instantly. It shrinks the weight of those easy correct events down to 0.08, and it massively bumps up the weight of its mistakes to 0.18. So what does that mean? It means the next model in line is mathematically forced to pay way more attention to those tricky coastal fires. And this right here is a rhythm you really have to remember. It's the absolute magic of AdaBoost, captured in one perfect sentence. Nothing about the data changed, only its importance changed. I love that. The wildfire events themselves are identical to what they were 5 minutes ago, but the algorithm has dynamically shifted its entire learning effort directly toward the unresolved problems. Think of it like you're studying for a massive exam with a practice test. When you're reviewing your answers, you don't keep staring at the questions you already got right, do you? No, those just fade into the background. Instead, you grab a bright yellow highlighter and you heavily mark up the ones you got wrong. AdaBoost uses this incredibly elegant exponential formula to do exactly that. The correct predictions get mathematically scaled down using e to the negative alpha, while the mistakes get vividly highlighted using e to the positive alpha. It literally hyper-focuses on the remaining mistakes for the next study session. Which brings us to our final part, section 5, the complete learning cycle. Now let's pull all of this beautiful logic together. We've seen the pieces, right? The weak learners, the alpha volume dials, the shifting focus. This whole thing forms an unbroken 8-step cycle that ensures absolutely no information goes to waste. We start by assigning those equal weights. Then we train our first weak learner. We measure its mistakes and calculate its alpha, its volume in our orchestra. Then comes the magic step. We increase the weights of the mistakes and decrease the weights of what we got right. We normalize everything so the math balances perfectly and pass that freshly highlighted dataset straight to the next learner. And then we just repeat. Every single mistake is embraced, highlighted, and mathematically woven right into the next round of training. But as we wrap up this explainer, all of this leaves us with a really provocative, honestly kind of dangerous question to ponder. If we just keep outing learners, endlessly chasing down every single tiny mistake, highlighting every weird outlier, when do we cross the line? At what point does the algorithm stop finding real, meaningful patterns and start harmfully memorizing totally random noise in our data? It is the ultimate balancing act in machine learning, and it's exactly the kind of thing you need to be thinking about before you unleash a boosting model into the real world. Thanks so much for hanging out with me for this explainer, and remember, always keep questioning the algorithms.